In the following, we are going to move on to two-dimensional systems. And the first two-dimensional system that we are going to try is the pristine graphene. So we open Quantum Honeycomp, and in here we select the 2D systems box. This will open up this window. In here we again can change the different parameters of the Hamiltonian. We can change the geometry between different lattices, and we can also add interactions. So the first system that we are going to try is, as I said, pristine graphene. So we press ground state button, we press bands, and we see the band structure of graphene. We can also calculate the density of states of this just to make sure that we all actually have graphene and that it's what we have. So the next thing that we are going to try is we are going to add a sublattice imbalance to graphene. So adding sublattice imbalance to graphene is the simplest way to simulate boron nitride. So the sublattice imbalance is this number here. We are going to put 0.3 for the sublattice imbalance. We press ground state, we press the bands, and we see this. So we have a gap in comparison with the pristine graphene case. And to make sure that we have a gap in the whole Brillouin zone, we can again calculate the density of the states, and yes, we do have a gap in the whole Brillouin zone. This gap in here, it has something interesting related with it, and this thing is that it has an anomalous velocity different than zero. So the usual way to see the anomalous velocity in a band is to calculate the Berry curvature of the band. And to do that, we just have to press this button here, Berry curvature, and we see that just in the K and K prime points, which are these 2 points in here, we have opposite anomalous velocities, or which is the same different Berry curvature. So something important is that this Berry curvature is opposite in sign. So when you sum up over the whole Brillouin zone, the result is 0. A case which has a different than 0 net Berry curvature is a model where you introduce both off-plane sigma splitting and Rashba field. So you calculate the ground state, you plot the bands, and you have this kind of messy bands in here. The important part is that when you calculate the Berry curvature, what you obtain right now is that your Berry curvature, it has the same sign across your whole Brillouin zone. And actually what happens if you calculate the Chern number of your system is that you have a Berry curvature located in the K and K prime point, and if you calculate the Chern number of this, you get a Chern number of 2, which means that in a finite system you are going to have 2 gapless edge states. So now we are going to move on to the interactions part of this window. So we will put pristine graphene again, but we are going to put electronic interactions as antiferromagnetic in the Z direction. We are going to turn on self-consistency. We are going to calculate the ground state and now the bands, and the system is gapless. So we add interactions to pristine graphene and the system is still gapless. However, if we are stronger interactions, so before we put an interaction of 1 times hopping, but if we move on to 3 times hopping, for example, and we calculate the ground state of our system, what we see now is that our system became insulating. If we calculate the magnetism of our system, what we get is something like this. So our system actually became antiferromagnetic. The important part is that this transition from non-magnetic to antiferromagnetic doesn't take place at any U. So you have to put a U larger than 2.2, 2.3 to get this transition between semi-metallic to insulating behavior. So this is all. Thank you very much.